Our next presentation, Responsive Parallelism with Synchronization, Stefan Muller, Carl Singer, Devyn, Terra, Keeney, Andrew, Neth, Kunal, Agrawal, Angelina, and Umut, Acar. And Stefan will be presenting the paper.
All right, thanks. So yes, this is joint work with many co-authors. Some of whom are here and who I might rely on later if your questions are too tricky. So primarily today I'm going to be talking about priority inversions. So if you're not that familiar or need a refresher on what priority inversions are, this is primarily a problem in programs where threads are assigned priorities, and the basic idea of the problem is that you have a thread that's at high priority waiting on a thread that's on a lower priority. And so the classic case of this is that, for example, if you have a low priority thread that takes a lock, and then the high priority thread attempts to acquire the same lock, and now it blocks on the low priority thread. So you have an inversion. And the high priority thread has to wait while the low priority thread does its work at low priority until it releases the lock. So in this case, this is what's referred to as a bounded priority inversion, because the priority inversion only lasts for the length of the low priority thread's critical section. So you might think that this is maybe not such a big deal, and it's often considered to not be such a big deal. But the problem is that we can take essentially any bounded priority inversion and turn it into an unbounded priority inversion by adding a medium priority thread here that now prevents the low priority thread from running at all, and therefore prevents it from releasing the lock. And so if the medium priority thread runs essentially forever, we've now caused a very large problem. So in priority inversions such as this that just involve mutual exclusion locks or mutexes, there's pretty typical dynamic solutions to relieve these problems at runtime. And so one thing that we might do is what's called the priority ceiling protocol, which is the one we study in the paper. And what this does is when the low priority thread has the lock and the high priority thread attempts to acquire it, so we're back in the situation we were in before, the runtime would realize that this is now the case, and it would promote the low priority thread to now run at high priority. So it's now running on as many processes as it can at high priority for the length of its critical section, so it can get to unlock the mutex, and now the high priority thread is free to continue its work. So that's great for mutexes, but in this paper we're mostly concerned with a more general, more powerful mechanism for synchronization called condition variables. So in the most basic case, a condition variable has two operations. So a thread can call wait on a condition variable or a CV to signal that it wants to block until some condition becomes true. Then when another thread establishes that condition as true, it will signal the condition variable, which wakes up the thread that's blocked. So in the presence of threads having priorities, now condition variables, blocking on condition variables, can also cause a priority inversion. So let's say that the high priority thread waits on a condition variable, and so it now goes to sleep. Presumably, the condition variable is going to be signaled by one of these low priority threads, and so maybe now we want to take that low priority thread and promote it to high priority, just like we did with the threads in the mutexes example. But the problem is, in the absence of any sort of static annotation or other information, we don't know which of these threads is eventually going to call signal. And so there's nothing the runtime can do. It's powerless to try and solve this dynamically. So the answer here is type systems or static techniques to the rescue. And so what we propose is a type system for preventing these kinds of priority inversions using CVs, which also kind of plays nice with using the priority ceiling protocol at runtime to prevent priority inversions using mutexes. We prove it's sound in a small imperative calculus, and then to show that these restrictions are neither overly exotic nor overly burdensome, we've implemented these as libraries and case studies in not one, but actually two mainstream languages. So first I'm going to talk through just several examples, the typing restrictions that we introduce at just a very high level. So the first insight that we use in our type system is to assign priorities to condition variables. So maybe we decide that this condition variable has priority low. Now what does that mean? Condition variables don't run, so they don't run at certain priorities. And indeed, at runtime, the priority of a condition variable does not have a whole lot of meaning. But it does have meaning statically at compile time in terms of restricting the threads that can signal on and wait on this particular condition variable. So the primary thing that we require is that the priority of a signaling thread has to be greater than the priority of the CV it signals, which in turn has to be greater than the priority of any thread that might wait on that. And so by transitivity, this ensures that the priority of any thread that might signal a CV is greater than the priority of any thread that might wait on this CV. These rules are just restated slightly more formally here with respect to a CV at priority row. And so it may seem that, okay, great, we've solved all the priority inversions. Signaling threads are high priority, waiting threads are low priority, you won't have a high priority thread waiting on a low priority, great. Of course, it's not that simple. And to show why it's not that simple, let's take another example. So this is an instance of the classic producer-consumer problem, but with a slight twist. So you have a low priority main thread that spawns these two threads at high priority. One is going to produce items that it puts into this buffer. The other is going to consume items from the buffer. And the two threads share a condition variable that the consumer thread waits on if it finds the buffer empty. So consumer thread finds the buffer empty, it waits on the condition variable, and then when the producer thread adds an item, it signals the condition variable so that if the consumer is waiting for it, it wakes up. So there's a bug here though, which is that as soon as the low priority thread spawns the consumer is high priority, and so now it gets the processors, and so the low priority thread may be blocked. And so the consumer thread then wakes up, starts trying to find items from the buffer. It finds it empty, and it locks on this condition variable. And so now again we have a priority inversion. And the priority inversion we have, and then maybe we also, for the sake of argument, have our pesky medium priority thread there. The priority inversion we have is actually not between these two high priority threads, the consumer and the producer. The priority inversion is actually between the consumer waiting for this low priority main thread to actually even spawn the producer. So we have kind of a second order priority inversion here. So we're going to fix that by adding another restriction, which I'm going to just kind of state informally here and motivate with a couple more examples. So the restriction is that if a thread has priority row, then obviously it can't signal a thread with priority greater than row, we said that already, but also its descendants can't either, so any thread it spawns transitively. So going back to this example, this means that the producer thread now can't signal that condition variable. It's at high priority, the condition variable is at high priority, but it is spawned by a low priority thread. And so now we've said that we're not going to allow this. Unfortunately now, in the absence of any sort of major restructuring of the code, we're now stuck in terms of getting this example to compile. So we introduce another mechanism called promote, which allows us to raise the priority of a condition variable at runtime. So now we've reordered the spawns, which is important here. So now the low priority thread spawns the producer, passes it this low priority CV, which is still okay. Because the low priority thread is allowed to signal a low CV. The high priority thread is allowed to signal a low CV. We're good so far. It then promotes the condition variable to high before passing it to the consumer, which is now allowed to wait on it because they're both at high priority. So it may seem kind of counterintuitive and dangerous to be messing with the priorities and therefore the types of objects that are in concurrent use at the same time. And indeed, this is quite dangerous in the absence of other restrictions. So to see just why this is dangerous, let's say that actually the producer is also at low priority. And so we've now sent that low priority CV to the producer, which we now promote to high priority. But now this signal in the producer is attempting to signal a high priority CV, which is not allowed. It was well typed at the time the producer was spawned, but it's not anymore, so we violated type safety. And in fact, what violated type safety is not this signal, it's actually this promotion, because we have now broken another thread's assumptions that it holds concurrently. There are ways of making this safe though, and these generally rely around ideas of ownership. So in particular, we're going to require certain operations, namely promote and spawn, to have some kind of ownership over condition variables. And specifically, we have ownership levels of each condition variable at each priority higher than the priority of the condition variable. So you can think of this as we sent the condition variable across the hall to the registration desk. It picked up a whole bunch of tickets for each priority higher than its own, and it's going to give them out. So at the moment, the low priority main thread has all of the ownership of this condition variable at all the priorities. And it's going to pass the high priority ownership to the producer, which it needs to signal this at priority high. It keeps the low priority ownership, and then it promotes it to high. Why does it keep the low priority ownership? Why is that important? Because I've said that the condition variable has ownership only at priority levels higher than its own priority level. So then when we promote this thread to high, its ownership at priority low should just no longer exist. So in order to do that promotion, the low priority main thread has to actually have the ownership at low so that when it does that promotion, it can throw that ownership away because that should no longer exist. So by separating this ownership into priority levels and distributing it to the threads that need it to signal and promote, we are now able to safely promote threads, condition variables that other threads may be using. So to show that this does successfully prevent the bad case where the producer is low, let's see what happens here. So the low priority main thread spawns the producer, and now because the producer thread is signaling the condition variable from priority low, it needs now the low priority ownership of that condition variable. But now the main thread cannot promote that condition variable to priority high because it doesn't have its ownership at low. It has given it away already. And so now it doesn't have the ownership of the condition variable it needs to do that promotion, and so that would not be well typed. So that's about all I have time to say about the type system for the talk, but obviously these are all fully formalized in the paper. So as proof here, I have a screenshot of a page full of horizontal lines and Greek letters. So please go see the paper for details. I want to briefly just spend a couple minutes talking about the soundness proof, and then I'll go on to the implementation and the case studies. So to prove that our system actually prevents priority inversions, we rely on formalization of priority inversions from our prior work, which talks about priority inversions as a property of cost graphs or dependency graphs. And in particular, we have the notion of a well-formed graph, which is one that can be scheduled efficiently using algorithms that just focus on greedily scheduling the highest priority tasks. And this corresponds to the notion of not having a priority inversion. So then to prove that well-typed programs do not actually have priority inversions, we develop a cost semantics that produces these cost graphs from programs in our calculus, and we've proven that well-typed programs yield well-formed cost graphs. So that is the one-slide summary of the soundness proof, and I want to move on and talk about the implementations and case studies. So since our type system relies heavily on ownership, we had the thought that maybe it could be encoded in Rust, which has some built-in notions of ownership. So we did this, and in fact, we found that with some of Kyle's C++ wizardry, we were also able to encode a lot of the restrictions in C++ as well. So both implementations essentially rely on representing CVs as objects with these priority levels, and also representing using kind of static aspects of the type system, the ownership levels that each thread has at each priority of that condition variable. And then our operations make sure both that when you split condition variables and pass them to threads, ownership is split appropriately, and of course that when you try to signal or promote, your thread has the proper ownership to do that. So in Rust, enforcing these things is reasonably straightforward. It doesn't exactly map on to the ownership system of Rust, but it is kind of built to handle these kinds of things with its affine type system, and so a lot of those restrictions are fairly straightforward. In C++, things are a little bit trickier. So we enforce that the programmer has to use only our operations, which do the splitting appropriately. And then we kind of poison all of the other copies of the condition variables that are lying around so that anything that wasn't gained by using our operations can't be used. And of course, in both implementations, what we've done is only sound as long as you don't use the trapdoors that both of these languages provide around the type system. So we've implemented a number of case studies to demonstrate the usability of the type system. I'll talk about two of them. So the benchmark that we have in Rust is a multi-user chat system. It's about 350 lines of code. So it models one server handling a number of concurrently connected clients. Obviously, this is a chat system, so we wanted to maintain high responsiveness to incoming messages. So all of the client handling happens at high priority, but there are also some low priority threads that handle writing some metadata to the channels. So initially, we actually had more priorities going on, but as we were building this in our system, we realized that the typing restrictions that we had applied actually had revealed a bug in our initial design, which we fixed by condensing some of the priorities. The largest benchmark that we studied was the memcached object server, which is an in-memory key value store. This consists of 20,000 lines of C code, which we ported to, so the original benchmark uses pthreads for concurrency. We ported it to use our system for both the type system and for handling concurrency and priorities. So most of the client requests are actually handled at an intermediate priority, and there's some logging performed at a lower priority. The highest priority operation here is actually occasionally the hash table grows too large and needs to be resized. So to make sure that this doesn't block other operations, we do that at high priority. So porting this code to use our library touched about 57% of the overall lines of code, which required about 80 person-hours of work. Most of these transformations, though, were just kind of mechanical transformations to make the code kind of fit into our framework. They weren't really detailed applications of the rules. So we anticipate that a lot of that work could be done by a suitable refactoring tool. So there's a lot more in the paper. In particular, I haven't talked about how the static typing interacts with the dynamic promotion of some threads to higher priority that this priority ceiling protocol is going to do. Of course, to also see the paper for details of the formal language and presentation of the type system, details of the soundness proof, and of course our other benchmark and more details of these. So in the future, while these implementations are really good for showing that these aren't exotic restrictions and they're not overly burdensome, it would be great to have a custom compiler that actually has full support for this type system and safe support, because both of these implementations actually use a little bit more user effort than we would have liked. Also, the synchronization mechanisms that we study, mutexes and condition variables, are quite general, and they can be used to implement a number of weaker synchronization primitives. So I have on here message passing, concurrent ML, many other examples. And it would be interesting to see if we could use maybe relaxed versions of our typing restrictions to incorporate these ideas as well. So in conclusion, we have a type system that rules out priority inversions with CVs and mutexes, so using static techniques for condition variables and using dynamic techniques for mutexes. We've proven it sound, we've implemented it in C++ and Rust, and we have some case studies that show the usability of it. Our artifact is available, so I hope you'll check out both the artifact and the paper, and I'm happy to take any questions.
Thank you. Questions?
Hi, Manos Capritos, University of Michigan. That was a great talk, first of all. I have a two-part question. Would it be possible to demote a CV? First of all, does it make sense? And second, if it does, like, would you need to keep around that low priority, that CV low that you threw away, so you can prove that you can demote it from, let's say, high to low, as long as when the thread ends, it gives you back, it knows like who spawned it and gives you back that high priority so you can demote it back to low?
Yeah, so we initially started looking into having a demote operation as well. And it, one side effect of that is that you actually also then need kind of dual restrictions on weight. So you don't, in the same way that you don't want to promote something that is possibly being concurrently signaled, you don't want to demote something that somebody else might be waiting on for kind of the converse reasons. So it required a lot of the same restrictions, just flipped. I don't think we worked that through all the way in terms of would it then also require getting back that low priority. I think it would probably be okay because if we assume that that low priority ticket was just gotten rid of, so if nobody's counting on it, then maybe we could make it reappear. But you do still have the you have to worry about concurrently waiting threads. I think the main I don't think there was anything conceptually really thorny about it. I think it just made the presentation trickier, and also we didn't really come up with a lot of good case studies that really needed a demote operation. We didn't see a great use for it.
Sounds good. Thanks.
Sure.
Well, I can think of a case where you might want such a thing.
Oh,
like
all right.
if you use libraries, right, then you push some of these things in libraries. Depending on the use of the library, it may be, different instances. So now you statically define a priority for the CV, but the library user may want something else. Can you think of a way to handle those cases?
So where you have defined a set of priorities and then you are using a library that defines things with other sets of priorities. So that is something that we've thought about, not necessarily in the context of this work. I'm still not certain that needs a demote operation. So a lot of things I looked into are for compositionality purposes, it's kind of unfortunate when a library hard-codes priorities anyway. So a lot of the kinds of libraries I've looked into, you really want to be almost priority polymorphic. But in general, if you do get the compositionality properties right, the most common case where we needed promotion was really in that example where you spawn a bunch of threads from a low priority thread, and then they just do their thing at a higher priority, and then you want to promote it. And so that was really, we thought for a long time about other use cases of this, and really that was the main use case of promote. But yeah, if anybody has, I'll definitely think more about that, and happy to talk offline if anybody has more ideas of use cases for promote or demote.
So you showed an example where you have multiple threads which all might signal. Do you have cases where you might have multiple threads which are trying to wait on a particular condition variable?
Yes. So multiple threads can definitely wait, and because we don't have demote, in the current system, waiting doesn't require any ownership at all. And so it's just the priority restriction that you have to be lower than the priority of the CV. So concurrent waiting is not a problem. And we also support, so there's another operation that I didn't mention called broadcast, which wakes up all of the threads that are currently waiting. And our system supports that too.
Thank you.
Devyn from Galma. I was wondering, so sometimes you have situations where you have objects that have their own priority settings, and I was wondering if there's any possibility in the system for dealing with basically heterogeneous polymorphism over this. And I assume the answer is no, but I wonder if you thought about that or how you might deal with it.
Polymorphism over priorities? Or
No, what I mean is, say I have a list of objects, and they each have a CV in them.
okay, great.
The objects themselves have some notion of priority because they're attached to some application thing that has priorities.
Yes, yeah.
Like their thread objects, for example. And then the CVs in them therefore also have to have the same priority, which is not the same over the entire list.
Right, so, yeah, so you're talking about, for example, a situation where you might want to pull the CV out of a list and signal it. Yeah, so we haven't studied that.
right, thanks.
Sorry.